This section is on geometric probability, but first we'll begin with a review of what probability is and how it relates to things that are non-geometric. So first of all, probability is usually expressed initially as a fraction and then maybe later on as a decimal or percentage between 0 and 1, and it is the desired outcomes of an event divided by the total possible outcomes. So it's what you want to happen divided by all the possible things that could. So if you want to find the probability of picking a club out of a standard deck of cards, there are 52 cards total, so that's all the possible outcomes is those 52 cards, and the desired outcomes is the clubs, and there's 13 of those, so your probability would be 13 over 52, or a quarter, or 25%. If you want to find the probability of not picking a queen, again, the total number of cards is 52, and you want to find out how many are not queens, so you take the total number minus the queens, and there's 4 queens, so the total is 52 minus 4. So not picking the queen, 48 of those cards. 48 over 52 is 12/13. Now let's consider a 6-sided die. If you want to find the probability of rolling an even number, the total possible outcomes for a 6-sided die, there's 6 faces, and the even numbers are 2, 4, and 6, so there's 3 of those, so 3/6, which is a half, or 50%. Or the probability of rolling a number greater than 1, again, there are 6 possible outcomes, and the outcomes you want are 2, 3, 4, 5, or 6, and there's 5 of those, so the probability would be 5/6. So this is some probability with cards and dice. Let's take a look at length probability now before we get to area probability. Here we have a number line with points A, B, C, D, E, and F on it, and we want to find the probability of landing on A, B, B, E, F, D, and then not on C, D. Now we need to have a total amount first. We can get the desired by looking at the segment lengths. We need a total for the total length of this. So we add 2, 3, 5, 1, and 4, and we get a total of 15. So the probability of landing on AB is the desired over the total. The desired is 2, the total is 15, so it's 2/15. The probability of landing on BE is, from B to E, is 3 plus 5 plus 1, which is going to be 9. 9/15 is equal to 3/5. The probability of landing on FD is 4 plus 1, so 5 over 15 is 1/3. And finally, the probability of not landing on CD is the entire number line minus CD, so that's 15 minus 5 over the total 15, which comes out to 2/3. Okay, now as far as length probability goes, because probability is a fraction, we can handle this in a couple different ways. If we want to find the probability of landing on the square out of this entire hexagon, we can make the whole figure bigger, we can make the whole figure smaller, but as long as these things stay proportionate, and they are, the probability doesn't change at all. So now the probability of landing on the square out of the hexagonal board is the same as if I do this. So strictly speaking, I don't need any segment lengths of any kind to do a problem like this. Now we'll do some later to make it maybe a little easier, but we're going to start off by not having any particular length at all. And so let me show you how we would do that. So here we have the same sort of figure. What I'm going to do is I'm going to make this distance here 2x. That will be the distance across the square. You can make it anything you want. You can make it x, you can make it 5, you can make it 27, you can make it pi. Doesn't matter. But we'll start off with 2x, and we always need to have an apothem and a radius. And notice that the center of the hexagon is not the top of the square or the center. Okay, now if we want to find the probability is always desired over total. So the desired is the square, the total is the hexagon. So basically we have to find those two areas and then divide them. So let's do the square first because that'll be a little bit easier. If this is 2x, we know this will also be 2x, and then the square is 2x times 2x, so that's going to be 4x squared. Now, if this is 2x across, we know that this distance here will be x. There are 12 of these triangles in the entire hexagon. 360 divided by 12 is equal to 30. So this is a 30-degree angle, which makes this 60. To go from a 30 to a 60, you multiply by radical 3. And then if we want to find the area of the hexagon, not the triangle, excuse me, first we find the area of the triangle, so that's half times the base times the height. And then you multiply by the number of triangles in the hexagon, which is 12. So times 12, and the 12 and the half is 6, so it's 6 radical 3x squared, and so the hex is 6 rad 3x squared. Now what we see is that the x squareds cancel, and so it doesn't matter what x was because it cancels, which proves the point that I made before when I made this whole figure bigger or smaller. And so there's your probability, which we can reduce to 2 over 3 radical 3. So that's the exact probability. You'd want to get a calculator to get a decimal or percentage to give it a little bit more meaning. But the main idea is to find out what figures you want to divide or subtract, as we'll see, and then go ahead and find those areas and do the calculation. A few more examples. Here we want to find the area which is in the triangle yet not in the circle, the shaded area. And so our probability is going to be the shaded area, which is triangle minus circle, and the total area is triangle. This time, let's give some lengths here. We could call things x as we did before, but let's give it some length. So what we're going to do is call this 1. So we've got a radius of 1. So our circle is pi times 1 squared, which is equal to pi. And now we need to find the area of the triangle. There are 6 of these triangles in the entire equilateral triangle, so 360 over 6 is equal to 60. So that's 60 degrees. That angle there is 30 degrees. To go from the 30 side to the 60 side, you multiply by radical 3, so that's rad 3. So our big triangle is a half times rad 3 times 1 to get this one, and then times 6 because there's 6 of them, and this becomes 3 radical 3. Half times 6 is 3 times rad 3. So our probability becomes triangle, which is 3 rad 3, minus circle, which is pi, divided by 3 rad 3. And you can't cancel these because this is add or subtract, it's not multiplied. So that's our exact probability. Again, you want to get a calculator and actually get yourself a decimal or percentage to give it a little bit more meaning. Okay, now we have the area inside the circle but outside the square. So this is going to be square, or circle minus square is our desired, divided by circle is our total. And again, we need to assign some values here. This time, let's say we'll call this distance here 1. That's not the radius of our circle. Notice that the radius of the circle is over here, also the radius of the square. Now, there's 8 of these triangles in the square, so I'll do 360 over 8, which is going to be 45 degrees, which makes this 45. To go from the short side, the 45, to a long side, the opposite the 90, in this type of triangle, you multiply by rad 2. And so the circle will be pi times rad 2 squared, which becomes 2 pi, because rad 2 squared is 2. And then to get the square, I do 1/2. Let's see, if this is 1, we know this is 1. So 1/2 times 1 times 1 times 8. So this one triangle is a half times base times height, and there's 8 of them. And I end up getting 4. And so my probability is going to be 2 pi minus 4 over 2 pi. And you can reduce that by dividing 2 from everything, so it's pi minus 2 over 2. So whatever that comes out to is your probability. That's the exact value, and then you get a calculator. Here we have a similar idea. Area inside the circle, outside the triangle. So we would do desired is going to be circle minus triangle, and the total is circle. So if I call this 1, this ends up being 30 here, 60 here. There's my 90. So this is, if this is 1, this is 2, and then this is a radical 3. And so the circle is pi times 2 squared, which is 4 pi because the radius is 2. And then for the triangle, it's a half times rad 3 times 1. So half times base times height of that one triangle, but times 6 because there's 6 of these in the entire equilateral triangle. And you end up getting 3 radical 3. So it's circle minus triangle over circle is going to be your area probability, your probability of hitting the blue area when you say throw the dart at the board.